what do waves do? They're a disturbance in matter. That's what they are. They transfer energy. And waves actually do work on stuff. Think about a beach. Think about sand. Who here has had the opportunity to stand in the sand with beach waves coming up on your feet? Okay. You're getting work done on you. You're getting little bits of work done on you. It's certainly doing work on all those little sand particles, because if you stand there long enough, of course, the sand all collapses out from under you. Because those little sand particles are getting work done on them by waves. There is energy in waves. And actually, physics of ocean waves creating green energy, which I now get to reference, you can harness the energy that's in waves. There are actually tidal energy systems. They're not real common. I don't know how many places they actually exist, but it's a fantastic idea because they're harnessing. What transfers energy to the ocean to have that energy end up in ocean waves? Huh? Okay, I think you were saying the right thing. If I can read lips. Did you say wind? Oh, okay. Yes, you did. Okay, good. Very good, Sarah. Wind. So wind, the power of wind creates the power of waves. Goodness gracious. And you're transferring energy. In each of those cases, you're transferring energy. So the particles of the medium don't shift. And this is where, again, I wish I had my big wave generator, because that would be just wonderful. The particles of the medium don't go anywhere. They just move back and forth in what kind of motion? Simple harmonic. So to demonstrate this, though I don't have my giant boxy wave simulator anymore, what I do have is a neat app called String. Let's go there. The rate of energy transfer of a wave is pretty much entirely dependent on the amplitude of the wave. So the bigger the wave, the more energy is transferred. And it's not a linear relationship. It's not linear at all. It's proportional to amplitude squared. So when you double the amplitude, the amount of energy that you can transfer goes up by a factor of 4. If you cut the amplitude in half, you divide the energy that's transferred by a factor of 4. What happens if you triple the amplitude of a wave?
You go up by 8? I don't know.
Energy transferred is directly proportional to amplitude squared.
Oh, 9.
9. Factor of 9. A wave that has an amplitude that's 4 times bigger than another wave has how much more energy? 16 times the amount of energy. This begins to give you a sense of, in the case of something like a tsunami, how much energy is transferred. If you've stood in surf, even if you've been to Lake Erie, if you've gone to Lake Erie and stuck your feet in the sand and felt water work on you, and on a windy day up at Lake Erie, it's forceful. You know, it'll pull you out. Think about a wave 10 times the size of a normal wave. How much more energy does it have?
A lot.
Numbers. 100 times, 10 squared. So yeah, it's got 100 times the energy. And this is an important point when we think about how waves transfer energy. It is not linear. It is exponential. So when you double it, you get 4 times the energy. When you have a wave 4 times bigger, you get 16 times the energy. You get the picture. So now we're going to talk a little bit about wave interaction. This is interference is the big thing we're talking about. When you have 2 waves that hit. When waves collide, there's the guy who does all the voiceover trailers for movies. He just died recently. When 2 waves collide, can they occupy the same space at the same time?
Yes.
Yes. Because they are not a matter of physical, they're not a physical object. They're just an energy disturbance to the particles, to the medium. So they can occupy the same space at the same time. That's called superposition. Okay. We can have superposition for mechanical and electromagnetic waves. Interference is a form of superposition. How many of you are familiar with cell phone interference? Okay. Where have you heard it? Okay. You can get a chattery noise on a speaker. And in the old system at the high school, we used to get that a lot. If people's cell phones were updating or people had stuff coming in their cell phones, we would actually hear it on the speakers. And I don't know why we don't get that now. I mean, we have a much better system. But we used to get that all the time. That's interference. That's because you have two electromagnetic waves that are interacting. And so one wave causes a disturbance in what you're getting in the other wave. You can have superposition in sound waves. Band, no, not band, band. You ever march and play
And it just sounds
at a
like
field where it sounds weird?
Yep.
When I was in high school, Latonia's field, they had one wall of the field had this weird old, it was like a bunker, I don't know what it was, but it had this metal wall. Well, metal bounces things really well, like light, hence why it's very reflective. A metal surface will also bounce sound very nicely. And as you got closer and closer to this thing, the band sounded worse and worse and worse because the sound waves would bounce off of that smooth surface and reflect back against the waves that were coming out from the band. And it sounded terrible. And they, you know. Have you guys noticed any difference with the new stands over here with all the aluminum? And you may not have. It's not, I mean, it's not like it's a wall of aluminum. I mean, they're oriented this way, but it's still a lot of metal.
A little bit of echo from the woods behind it. Like when we were facing this way, it was just like open space.
Yeah.
So it wasn't too much echo. Now there's like a little bit of echo.
Okay.
Because
the wood is less bouncy. The wooden surfaces will bounce sound less than the metal surfaces will. Okay. So we can do superposition. We can do interference. And I used to rig up a ripple tank for this, but I don't have an overhead projector anymore. I need to go buy one used. And I thought one was being saved for me at the old... Okay. So we have constructive and destructive interference. Most often what we actually get is something that's neither complete constructive or complete destructive. This depends on all of the crests and troughs being lined up perfectly, either together or in opposition. What's most common is some far weirder pattern. So we're going to practice actually drawing a resultant wave. What we get as the resultant, it's called the resultant wave, is what we get when we have two waves that interfere with one another. So let's try that. Okay, so I've got a nice sort of generic, more or less sinusoidal wave. And I've got my zero. I should actually put that in as a red line. That's probably helpful. So that's my zero. Whoops. Okay, and I've drawn a second wave in on top of it. You're going to be hard-pressed to do an exact copy of this, but we'll do a little bit of practice with these. I just want to show you the basics. So let's say we're going to look at the interference pattern, and we'll trace out the new wave in green. Green will show up nicely. So at each point on this wave, we're actually going to add the magnitude of the disturbances. So here, let's see, and I guess I can finish that. Okay, so we're going to look point by point. So at 1, oh, that's terrible. So at the 1 mark we have, we'll call this negative 0.25, and here we'll call this negative 1.5. So what would that give us? Maybe that's 1.75. I'll expand it. That would give us a point that's somewhere down around here. So they're interfering constructively or destructively? Constructively, because their magnitudes have the same sign. So it is the displacement of the particles at this point are farther in the same direction. This, this one is, we're saying like negative 0.25. We're calling this one negative 1.5. So the resultant is negative 1.75. The resultant wave has a displacement that's actually greater magnitude than the displacement for either of the first two. Does that make sense? I think it's going to make more sense as we go through this. Okay, so I'm going to get rid of all my extraneous stuff here. So we have our first point. Oops. Okay. For our second point, what do we have? Maybe negative 1.25 and negative 1.5? Probably. So I'd say that that's probably there again. Here, maybe negative 1.75, 1 to negative 2.5. So what would that give us as a resultant? Negative 3, negative 4.25?
Why is the last one right there?
1 point. Oh, you're right. I screwed that up. If I hadn't tried to do that in my head, it would have all been fine. So if that's negative 1.25 and that's negative 1.5, that makes negative 2.75, huh? Does that make more sense? Sorry about that. Okay. So here we've got negative 1.75, negative 2.5. When you add up those displacements, because that's what interference does, it adds up the displacements of the particles at a point in a wave. What would we get? Negative 3, negative 4.25. So 1, 2, 3, 4. Negative 4.25. So, is this constructive or destructive interference? It's constructive. The displacement of those particles is larger based on their interaction than it is based on either wave individually. We're starting to see an actual curve. Okay, let me get rid of my little notes to self here. We're going to start to see, well, actually, we won't start to see, we'll start to see destructive interference very soon. Okay, so on our next point, you know what, we're going to go ahead and call that 0, actually. My red line is badly drawn, but the black line pretty much crosses through the 0. So we've got 0 there. What do we have here? 1, 2, 3.25. If that's 0, guess what? We actually get a dot on one of our original lines. We get a point. Okay. At our next point, and here's where my line is badly drawn, we'll take this, and this. So this is probably 0.5, and it's positive. It's above the axis. 1, 2, 3. This is negative 3.5. So negative 3.5 plus 0.5 gives us 3. Is this interference constructive or destructive? Destructive. Because suddenly we have a magnitude, or we have a displacement that is smaller than the magnitude of one of the waves. They're starting to cancel one another out. One has a positive displacement, that 0.5 positive. One has a negative. And if we look at it, and interference patterns look really weird. They don't look like a normal wave. And it doesn't help that I drew this sort of freehand and willy-nilly.
You said when we first started off that was constructive.
Yes, because they were adding together.
So it's destructive now.
Now it's destructive. That one point is destructive because the magnitudes are in opposite directions. So we had a positive displacement on one wave and a negative on the other. So the magnitude here of the resultant wave is less than the magnitude of one of them. So we're now starting to see them canceling one another out. So looking at the next point, we have this, and we'll call that just 1. So we have 1, and we have negative 1, 2, 3, negative 3.5 again. So negative 3.5, negative 1, what do we get? 1, 2, something like that. Constructive or destructive? Destructive. Because
as long as both of the lines are on either side of that red line.
when they have different, no, because we can have, let's think about that some more. Let's do this one and then talk about generalizing from the specific. Because I'm always hesitant to say always this or always that.
Yeah.
Yeah. So I'm trying to think through cases of, yeah, we've only done a few points on this. So let's.
It's just what I'm seeing so far is that's what my mind jumps to.
That's, yeah. You want to jump to yep. Okay. So I'm just starting to sort of connect those dots mentally. Okay, on the next one, we have 2 and 1, 2. Let's call that negative 2.5. So what do we get for our resultant? Negative 0.5. So here, you know what? I have to. Let's not assign constructive and destructive to individual points yet. Let's look at the overall pattern that we start to see, and let's think about the desire to generalize. Okay, so let's just sort of do. Let's do the wave and then assign it. Okay. Okay. On this next point, we have. You call this negative 1.75. We'll fudge and call this 3. So what do we get for a magnitude?
So are you just picking points?
I'm just going down each line.
Okay.
Yeah, I'm because that's the easiest way to do it. Is actually looking at where it intersects an even number on the x-axis and then looking for the y value. We could do something in between the values on the x-axis, but it would be even tougher. Well, so here would be the other thing you could do, I suppose. You could look for places on the x-axis where the line crosses exact values on the y. So that would be the other way to do it. I'm just doing the even values on the x. Okay, so what do we get for our resultant here? 1.25. So let me get rid of all these guys. And so here we've got, they're so far apart I actually have to do that. So 1, 2, 3, 4, 4.25 and negative 0.75. And yes, I am sort of rounding and fudging a little bit, going by quarters. I'm not going to go into 0.6s and stuff. I don't think I can estimate that well. So what would our resultant value be there? Am I on the same line? No, I am not. Oh, yeah, okay, I am. 3.5, so 1, 2, 3. 0.5. This resultant is pretty darned weird. They tend to be. I mean, you took two more or less regular sine waves, as regular as I could draw them by hand, and what you're getting is this very irregular pattern. Yes, sir? So here we have two, and again, these are supposed to be perfectly regular sine waves, as good as I can do. The last ones were definitely irregular. These are in perfect alignment and perfect total destructive interference. There's nothing left. They wipe one another out. Anybody have a white noise machine at home? White noise machines? Have you heard of them or seen them? It's a little device that's supposed to cancel out other sounds because it creates a disturbance in the air. It creates a sound wave that cancels out a lot of other sound. They have noise-canceling headphones. That's acting on the principle of total destructive interference. So if we look at an opposing case where we have a perfect sine wave, let me draw it. So here we have two sine waves that are perfectly aligned, okay? And if we go through the process, and of course I didn't line this one up as well as I wanted. There, that's better. Okay, if we go through that same process that we started off on with the most complicated case possible, brilliant, and we add these points. So here we have 0, and we have, oh, none of that lined up when I moved it, hold on. So if we add up those magnitudes, here we have 0, and we have 1, 2, 3, 4, 5. So that's gonna have a spot right there. Well, here we have 0.5 and 1, 2, 3, 4, 5, 5.75. So that's going to give us a spot right here. At this point, you're starting to see that the magnitude of the resultant wave is larger than the magnitude of either of the contributing waves. Okay, so here we get one, let's call that 1.5, and 2, 3, 4, 5, 6, let's just call that 7. So if we've got 1.5 and 7, what do we have? 8.5. 1, 2, 3, 4, 5, 6, 7, 8, 8.5. Okay, not in the middle at all. Constructive or destructive? It's the magnitude of the resultant is larger than the magnitude of either of the two contributing waves. And we're starting to see this larger wave emerging. Now, what you're going to get here, and this one's easy because they're well lined up, so I can kind of sketch this out without doing the pain in the tuchus point by point. We're going to start to see something that looks like this. Okay, as a generic. Not in the middle at all, because we're adding the magnitudes of the disturbance. So this is going to be total constructive interference. There's no point where these two cancel one another out. Every single point on either of those wave lines is additive. And I'm getting closer to going with Zach's generalization that so if they're on the same side of equilibrium, it's constructive, but I'm not there yet. Because you can have waves that start at different locations like we're showing here. Constructive and destructive always seem really simple, but it's actually a little bit trickier. It's only tricky. Okay, here's the case where it's tricky. It's not tricky conceptually. It's tricky when they don't line up well. So when they don't line up well, you get this mess of a wave pattern that doesn't really jive with any of our notions about constructive and destructive. Understanding that's easy. And I think understanding that's easy. I think looking at two waves that don't line up is weird. And you're right, it doesn't occur right in the middle of the two, and it won't. Okay, let's step back to, hold on. Constructive interference, when you have two waves that are superimposed in the same direction, and this does kind of get to Zach's universal generalization, which I'm still not totally comfortable with because I always hedge my bets. But and that you want to make sure that you understand that it's the magnitude of the resultant is larger. So you can have a larger magnitude in a negative direction, it's still a larger wave. Some of the individual displacements give you the magnitude. Now, when we say this is only valid for waves with small displacement, once you get into really large displacements, you get so many, you get interference and reflection, and you get all these other small patterns happening that kind of throw off the simple mathematical, oh, negative 1.5 plus 2 gives us, and it doesn't quite work anymore. So this really, best applied to small waves. Factors sort of rapidly spin out of control once you get into much larger waveforms. There's this idea of resonance, and we won't get to talk about it a whole lot because we don't do the sound chapter anymore. But resonance is this idea that materials have a natural frequency that you can get interference going and the wave becomes self-sustaining.
Like singers who break glass with their voice.
Singers who break glass with their voice, right, because they can hit a pitch that the glass naturally would vibrate at, and you get this self-sustaining wave, and it's enough vibration to actually shatter glass. Okay. With that, if you aren't familiar with XKCD, you should be. Excuse me, you're jiggling your leg up and down. You ever sit next to somebody who jiggles? And the whole floor vibrates. It's traveling through the floor and making my desk resonate. Oh, I'm sorry, I didn't realize. I'll stop. Actually, can you just shift the frequency up by 15 hertz? I think you can get resonance with Steve's desk instead. Here are the calculations. Let's coordinate and try to spill his drink. I love XKCD. It's labeled as a comic of math, sarcasm, and romance. You should just read it every day. It comes out 3 times a week, Monday, Wednesday, Friday. You should just always check XKCD. Okay. So the other kind of interference, of course, is destructive. And what we get is a magnitude smaller than either of the ingoing waves. Again, it's just the sum of the individual displacements. If they're equal and opposite and perfectly equal and opposite, hey, it's 0. It cancels out. The math is simple in a single pulse wave. Like I said, if we go into something like this, and we've got sine waves that are not well superimposed, and it's complicated. And we don't like doing them, but we do them occasionally. Okay, so with that, what we're going to do, because I don't want to start talking about standing waves until tomorrow, so we're going to take the big spring out in the hall, and we're going to have you watch interference patterns.